Well, good morning, everybody. Um, Wanted to introduce myself. My name is Mark Enochs. I'm with MNX Inc. here in the Minneapolis-St. Paul area. And we're a manufacturer's rep firm. And so we represent a number of different manufacturers across the upper Midwest that make various water and wastewater technologies. And I'm going to introduce Moleaer to you this morning. But before I do that, I wanted to give a little bit of relevant just a few thoughts. So before I became a manufacturer's rep, I was a consulting engineer and worked for CH2M Hill, which is an international engineering firm. Back a few years ago, probably 8 years ago or before that, in that time frame, CH2M Hill was hired by the Riley Purgatory Bluff Creek Watershed District to be their engineering consultant. And so for over 5 years, we as in CH2M Hill was the engineer for the watershed district and handled all the technical aspects and strategy and so forth for cleaning up the lakes. It's a 48 square mile watershed district and has 3 creeks or rivers that run through it and about 13 lakes and hundreds of stormwater ponds. And as the chief engineer, we led the crew to developing technologies and approaches to cleaning up the lakes. Everybody said, "Hey, when's our lake next? How can you clean it up? What needs to be done to clean our lakes up?" Because there's a lot of algae just based on nutrients that got into the water column. And so our engineers and scientists dug into that question and spent years developing an approach and strategy and basically ground truthing the technology needed to clean up the lakes. Now, the lakes in that area, it's in the Chanhassen, Eden Prairie, Minnetonka area. The areas around most of the lakes and ponds are pretty well developed with neighborhoods and rural neighborhood communities around them, and so the answers that I'm giving and the information we're giving are specific to those lakes, but this could apply to a lot of the lakes in your area. So we just found that the lakes year to year just had a lot of foggy water, green water, a lot of algae, and a lot of nutrients. And what that did is impeded people's desire to be in the lakes. People didn't want to swim in them, didn't want to boat in them, and they still did in some cases. And throughout the year, throughout the warmer months, the levels of clarity would come and go sometimes, and sometimes they would get worse in the warmer months. But just a few things to lessons learned, and then I'll turn it over to Moleaer. The video you just showed, Maddie, was fantastic. I worked with Prajimic and the carp folks for years. They did a lot of research in the district's lakes and the importance of the carp. In each of these lakes, we learned that we've got to balance the ecosystem from a fish standpoint, because the carp get in, they're bottom feeders, and they will dig up the bottom of the lakes. And so what happened is the nutrients are in the bottom of the lakes and the bottom of the stormwater ponds. And if the carp get in and churn the bottom of the lake up, that releases the nutrients into the water, and they just grow, and it misbalances the ecosystem, and nutrients take off and the levels increase. So carp first. So getting control of the carp to make sure they're not going to destroy the bottom of the lake was an important first step. From there, we did a number. What we found, the short story is, we found that the lakes basically the nutrients were coming from the bottom of the lake. There's a bunch of muck and sediment in the bottom of each of these lakes and in the stormwater ponds that have gotten there over the years. We did core samples into the bottom of the lakes and the stormwater ponds and we looked at 3 or 4 feet of the sludge in the bottom of the lakes and the sediment at the bottom. And that core sampling showed that the stormwater systems are working really well, that the sediment that ran off over the past decades as the areas were being developed was already there, and it still is there, and it's still belching out nutrients. And what we also found, and we went back to Civil War, it was like around the 1860s and 70s, and looking at the different sedimentation layers in these lakes, and we could see when each specific lake developed and the area around it developed. And we're like, oh, that's when Highway 5 was put in, because the runoff was changed the characteristics of the sediment, and there are different bugs and so forth in that sediment. So the short story on the core samples it showed us that the stormwater systems are working, that there was no need to control the runoff anymore into the lakes, because that's not the source of the nutrients. So rain gardens and street sweeping, those are great practices, but they did very little to nothing to controlling the nutrients going into the stormwater ponds and the lakes, because the sediment was already at the bottom and it just sat there in the bottom and belched out nutrients. So we said, well, if we got oxygen or air down to the bottom of the lakes to prevent the bottom of the lakes and the ponds from going septic and getting all stinky, and would that control the nutrients? And we found, yes, we found time after time that that is the case. We did pilot studies with a technology similar to Moleaer before Moleaer was even a company. And we proved that pulling water out, adding oxygen, and putting water back into the bottom of the lake, that actually kept the nutrients from being released. We also did studies during the winter months, or when the sediments in the bottom of the ponds basically concentrated because ice was on the lakes and the ponds. And during the winter months, the nutrients continue to build and build and build and build until the springtime, when the nutrient levels would spike. The ice would come off, the winds would mix the lakes and the ponds, and nutrients would go crazy. They're extremely high levels of nutrients. And then the nutrient levels would be high in one lake, and then would flow down to the next lake, and then you've got a big soupy mess of green, unhealthy water. And so we found that by adding oxygen during the winter months, that kept the nutrients from releasing from the bottom of the lake. And we did that in Lake Ann, and did a couple winter pilots to prove that that actually worked, and just by getting air down to the bottom of the pond. So those are, and then we actually loaded in to a different pond, a different lake. We loaded in liquid oxygen that spread across the bottom of the lake. And again, instead of putting alum in or some other thing to keep the pond intact, the bottom intact, we put oxygen there, and that took care of that natural process, and did it organically or naturally, just by having oxygen down there. So that is a kind of a long-winded introduction to Moleaer, because I was thrilled as I became a manufacturer's rep and switched from consulting engineering and watershed engineering into the equipment world. Moleaer is a company I found, and they actually have figured out how to do what we had cobbled together years ago in Mitchell Lake, and that is, how do you get water saturated with oxygen, and how can you introduce that to a water body like a lake or a pond? So Moleaer has figured out how to do that, and they're doing it all over the country. And with us today, we've got Moleaer. And Moleaer is a company that's been around for a little while. And Christian Ference is with Moleaer. He is a senior water quality engineer, and he is part of Moleaer's application and development team. He's got a background in chemical and environmental engineering, and he specializes in surface water applications and special application developments for Moleaer. So if there are no questions, I will turn it over to Christian.
Mark, thanks so much for that introduction there. It's actually very relevant, especially to one of the case studies that we're going to present today, that I'm going to present to go over this morning about actually the combination of different technologies, such as CARP, for example, for an integrated approach to management, so lake and pond management. So I'm going to go ahead and pull up my screen here. All right, let's get into this. So again, my name is Christian Ference. I am an application engineer at Moleaer, and I work primarily on our surface water applications, looking at the use of nanobubble injection in lakes, ponds, and other surface water applications, and also that overlaps a lot with our irrigation water work, which is certainly very prevalent here in California, where we're based, and then also in a lot of our applications in Europe and South America. But I do specialize and focus primarily on our surface water applications, and really what we also term as clean water, and then also look at special application development. So that's where we're looking for the application of nanobubbles in markets that are perhaps a little bit tangential to where we primarily work, or where Moleaer primarily works. As a brief summary or overview of what we're going to look at today, I want to give just a brief background on who Moleaer is, what it is, what we do, and what we're really working with this new nanobubble technology. And I'll give an introduction briefly talking about the equipment that is produced by us, and really how this is designed for the different various applications where nanobubbles can create value. And then I really want to do a bit of a dive into just the science behind nanobubbles, providing an introduction to what this technology is, and hoping to develop a level of familiarity with the nanobubble itself, just give a sort of scope on just how small of a particle that we're working with, and also how it's effective at really delivering oxygen into different environments. And then we're going to finish up today going through various case studies and applications here, looking at where these have been applied in the real world, and how they've been used alone and in combination with other technologies to achieve that oxygenation effect, as well as some algae control case studies here as well. So as I mentioned, Moleaer focuses on sort of a couple different markets or applications here, and three broad level applications are really core to the business. We look at from a high level of food, water, and natural resources. And when I say food and water, we look at food in terms of the use of the injection of nanobubbles, primarily in the irrigation water, whether that's a pre-treatment, if irrigation water is being pulled from a nearby pond, lake, or basin. Sometimes it's even a stormwater retention basin that's being pulled into, say, a greenhouse. We're looking at the pre-treatment of that water so that it's more effective in horticulture applications. When we talk about water, it's primarily algae control. And again, pre-treatment, we typically talk about, say, drinking water reservoir treatment or pre-treatment when it comes to water applications. We also work in actually wastewater treatment applications as well, using the bubble for facilitating separations applications. And we also do a good bit of work in natural resource recovery, but we're not going to focus too much on that today. The company Moleaer was founded in 2016. We're based out of Los Angeles, California. And that's where both my team, our applications team, and the research team, corporate is located here, as well as all of the equipment for Moleaer is manufactured rather here at our Los Angeles headquarters. We are working with a patented technology, and that's we first launched the actual nanobubble generation system in June 2017, and we've been working to develop the markets around this in both food, water, and in resource recovery over the last several years. We do now, one other thing I'll highlight here is we do now have over 1,200 installations and 1,200 installations, and we're not only working now in the United States, but really all across North America and in Europe and in South America primarily as well. And over the last couple of years, and this is largely through our team, the applications team, we've worked to not only develop and commercialize the technology, but also develop close partnerships with various different research and organizations and universities, both here and in Europe. And just to name a couple that we work closely with, we work with Georgia, University of Georgia, Arizona State does a lot of research on oxidation, which we'll cover here shortly, and even nearby universities such as UCLA, who does a lot of work in water research. As a high-level review of our technology here and the way that we've packaged this to be relevant to different markets and applications, briefly touch on the product line here. In the upper left-hand corner, we have the Clear, and this is a outdoor rated nanobubble generator. It's really to sort of the set and forget form of the nanobubble generator that can be located outside. It's meant to be really unobtrusive in outdoor environments, located next to, so it's onshore, next to a pond or a lake or any other surface water body. And it can provide that 24-hour continuous water nanobubble injection. And we can orient this such that we're injecting nanobubbles towards the surface of the water, or utilizing piping. We can direct that oxygenation and the nanobubble solution down towards deeper areas of the water body, depending on the treatment outcome that you want to achieve. Now that unit injects primarily air, and also can be equipped with an enriched air system, which is just 40% oxygen if there is a need for an additional amount of oxygen in the application. The other product that I just want to briefly talk about is the Neo product, which is in the middle on the top. And this is primarily focused on greenhouse and aquaculture applications, although it's becoming more relevant and more widely used even in surface water applications, primarily because this has an onboard oxygenation or oxygen generator. And in that case, in applications where really an even higher amount of oxygen is required, and in cases where we even would like to achieve supersaturated oxygen conditions, which again we'll get to here in a case study in a little bit. Because this has an onboard oxygen generator, this system can really provide that high level of oxygen delivery to, in this case, an ecosystem, pond, lake, or a reservoir. And that can be really relevant in the applications where, as Mark referred to, we have that severe limitation of oxygen in the system. And we're really looking to supplement the oxygen available, especially in deep water at a pond and a lake, to facilitate natural microbial processes. In the upper right-hand corner, we have the Optimus system, and this is really just based for high flow systems. So in cases where we need 500 or 1,000 GPM or more. And the other thing that I'll mention just briefly is each piece of equipment can be remotely monitored. So we can monitor the performance of that equipment from your computer or your phone to look at the performance and the status of that equipment in real time. So that was a brief introduction on the company and the technology that's actually produced. But as for the technology and the science behind the nanobubbles, I really want to spend some time today focused on this And to just, as I mentioned, to really build some context around what we're working with. So I want to talk about nanobubbles not only for oxygen injection and the use of the Moleaer technology to achieve that efficient oxygen injection and delivery into various aspects of a water body, but in addition to that, I really want to focus on why is that distinguished with nanobubbles itself, and why is this exciting? So the first thing to know about a nanobubble is that it's small, and that's probably rather intuitive from the name. But I want to provide some context as to just how small we're working with. So in the case of diffused aeration, which most of us are probably familiar with, we're primarily working with what we term as micro or fine bubble aeration. And the micro bubble, or in the fine bubble aeration, this would be primarily what's generated from a diffused bottom aerator. And this bubble is a couple hundred microns, all the way up to a centimeter, can be even larger. And these bubbles are rather inefficient at oxygen transfer. As we're all aware, the primary, one of the really primary benefits of this diffused aeration is really just mixing water, because these bubbles are very buoyant, and that buoyancy is just a function of the size of that bubble and its ability to rise through the water. And because of the high volume of this bubble to the surface area, meaning it contains a lot of gas compared to the surface area of that liquid gas interface, it's not able to transfer much of that gas to the water. And so it rises to the bubble, rises to the surface of the water, and releases that gas to the atmosphere. As we go down a couple orders of magnitude in size, we get into micro bubbles. And these can be exciting because they can be quite efficient at gas transfer. So that gas transfer, as I mentioned, is a function of the surface area of that bubble, meaning how much of that gas in the bubble is in contact with the liquid around it. Because that micro bubble is much smaller, again, up 2 to 3 orders of magnitude, 100 to 1,000 times smaller than that fine bubble, it can be much more efficient in gas injection to the water. And for context, that micro bubble can be around the size of most plant and algae cells. But even still, this bubble still has significant buoyancy and rises to the surface of the water. And most of that gas, even with microbubble injection, is still released to the atmosphere. And it's primarily when the bubble rises to the surface, pops. One thing to note about microbubbles is that they are sort of well known for an appearance of cloudy, or sometimes called milky water. And this is a byproduct of that microbubble injection, but is very different from what we're working with in nanobubbles, which are, again, if we go another order or 2 of magnitude smaller, is what we're working with here. So the size of the bubble here is very important, because once you get to that nanobubble size, that bubble begins to exhibit really different behavior than the bubbles that than their larger bubble counterparts. And when I say different behavior, the nanobubble itself is actually not, or what we call neutrally buoyant, meaning that it does not rise to the surface and burst, but rather kind of hangs out in solution and has a very extended longevity in water, because its motion is driven by Brownian motion. So that allows it to be distributed around a water body, primarily driven by natural currents and also by Brownian motion. But that does help with the facilitation and delivery of oxygen to different parts of the water body. For context, this is around the size of a lot of bacteria and even some very large viruses, or for something that may be a little bit more easy to sort of wrap your head around, about 2,500 times smaller than a grain of salt. And there's a couple other really exciting properties of the nanobubble that I'm going to get into here in a minute. But the first and foremost, most important aspect of them, just to understand, is just how small they are. We have a sort of a visualization of the behavior of these different bubbles on the left-hand side here. We have the larger bubbles, which rise, the fine and micro bubbles, which really do rise to the surface and release most of that gas to the atmosphere. And I just want to emphasize that is important, because the amount of gas that's transferred, in this case oxygen, that's transferred from that bubble to the liquid around it, or the pond or the lake is really what's creating value. It's what's helping the push forward these biological and chemical reactions, which are really desirable to help ponds and lakes overcome high levels of eutrophication from high nutrient concentrations. So, as I mentioned, the bubble is primarily known for its small size, but it actually has a lot of different properties, which then translate into different behaviors in a water body, which can be very attractive for water body management. And that bubble, when we get to this really small size, does not perhaps behave like its larger bubble counterparts, in that it actually has a very high internal pressure, and then also because of that is balanced with a high level of surface tension and behaves almost like a particle. And so it behaves with a hydrophobic particle and therefore has a strong charged surface. A nanobubble is known to be negatively charged, although that charge can be influenced by other components of the water body. So in some cases, if we're working in a very clean laboratory environment, that bubble will have, if there's nothing that's bound to the surface of it, will have a rather strong negative charge to it. But if we're working actually in a natural environment where there's all sorts of different things that can influence and bond to the surface of that bubble, we can see that bubble exhibit either negative or positive charge. And that really influences what it reacts with, especially in terms of reacting with algae and generating an oxidative impact. And the one other property that I want to sort of emphasize here, and it's particularly relevant to a lot of the applications in surface water and ponds and lakes, is this high gas transfer efficiency. And the nanobubble production process is inherently a very efficient gas transfer process, especially if we're using oxygen as a supply gas source. So that would be, for example, in the NEO product, using an onboard oxygen generator, which we're actually then taking that oxygen, compressing it, and injecting it directly into the water. So in that water, when that perhaps anoxic water is coming into the NEO from the surrounding environment, and then going through the nanobubble generator, it is both being filled with a sort of saturated solution of oxygen nanobubbles. But in addition to that, in that nanobubble production process, you're also dissolving a lot of that gas into the water. So you actually get gas in two different states. You end up with gas or oxygen that is dissolved, and that's the oxygen that we, the type of dissolved oxygen that most of us are familiar with. But you're also ending up with oxygen that is actually suspended in the nanobubble form, and that behaves very differently, and is really critical to the outcome of the applications that we have in surface water. Now, the various properties that we just walked through then do translate into the behaviors here that we have listed on the right-hand side. So that bubble, as I mentioned, it is neutrally buoyant. So in that water, if you look at the discharge of a nanobubble generator, you'll see, what you're not seeing actually is the nanobubble injection. And the nanobubbles exist at approximately about 10 to the 8th concentration or bubbles per milliliter. But the bubbles are so small that they're not actually visible to the naked eye. But as part of that nanobubble production process, we're actually seeing sort of what we call a polydispersed size of bubble production. And so in the discharge of a NEO, for example, you would see some larger bubbles formed in that discharge, but primarily you're getting a saturated solution of dissolved oxygen and nanobubbles. As those bubbles are injected into the environment, they are stable and long lasting. Now that on the laboratory side, we're looking in a very clean water environment where the bubble does not have anything to react with. For example, there's no contaminants in the water that may bind to the surface of the bubble, or there's no strong oxygen demand, either from chemical oxygen or biological oxygen demand in that water. That bubble has an extremely extended lifespan, and they've been identified to last for up to months suspended in solution. However, that's in a clean water environment. when we work in with that real world pond or lake application, that bubble has a reduced longevity from that, weeks to months. It is reduced because it is either transferring gas to the surrounding environment as applicable, or potentially reacting with other components of whatever may be in that water that we're injecting into. And because of the charged surface that we measured, or we mentioned in the nanobubble property, and as I noted, that bubble does have a negative charge, again, in a clean water environment. But what we do know is that that charge can be flipped depending on, say, pH or other components of the water, which compounds in the water that may bond to the surface and flip that charge from negative to positive. But this surface charge actually creates a really important behavior of the bubble, which is it generates an oxidative impact, meaning that as that bubble collapses, and as I mentioned, it's a high pressure system, so it contains a lot of energy. As that bubble collapses, that energy is released, and that energy inside the bubble is released in part as oxidation through the generation of reactive oxygen species. And we'll get into what that really means here in a little bit, but it does play a key role in how the bubble helps facilitate algae control, and also helps create an oxidative environment that's beneficial to the microbial and chemical behavior in ponds and lakes. As a brief description of what our team honestly ends up doing a lot of testing with is we have an instrument in-house called a nanosite, and we work with this piece of equipment which actually is able to quantify particles of the nanobubble size in that 100 to 200 nanometer size. And what we're able to do is take a sort of control sample of water where we see a low concentration of particles in that 100 to 200 nanometer range. And after you're processing it through our equipment and recycling it through the equipment, recirculating it through the equipment as you do in a pond or lake, you see that particle concentration increase. And we're able to measure we're able to measure that increase in nanoparticle or nanobubble concentration. And then in addition, a lot of the research that my team does looks at how does different water quality parameters influence the rate of generation of those particles, or the nanobubbles.
Hey, Christian.
Yeah.
Hey, quick question. Somebody wants to know, has there been any testing conducted on acute toxicity levels for freshwater organisms?
That is a fantastic question. So I in the beginning of the presentation, I do like to give a brief introduction to some of the applications that we work with, whether that's in food applications, meaning in horticultures and greenhouses and aquaculture. And the bubbles, there's a couple of research papers out on this actually, and this is also in addition to what we've observed in the field. There's no level of toxicity to higher level organisms, meaning that we've not seen, at least at the concentrations of bubbles that we're achieving in the field, any negative impacts on plants or in fish, for example. And I know there's some concerns about fish with, say, gas bubble disease, but especially at the dissolved oxygen levels that we're working with in ponds and lakes, and due to the nature and behavior of the bubble, there's not a negative or toxic impact that we've observed. If there's any specific organisms that would be of interest, I'd be happy to follow up. We could pass that along. In terms of the technology itself, so we have a diagram on the left-hand side here, just to show really the simple components of the process and to really pair back what's inside of the equipment that we're working with. The nanobubble generator does require a flowing stream of liquid. And in this case, often the units that we apply in surface water, it's utilizing a pump that Moleaer is providing to create that flowing liquid. But if there are applications where there's already existing pumped water, and that's actually something we find fairly often, especially in managed water bodies, then we can actually take advantage of that liquid flow and plug one of our systems directly in line on that. And then once that system's in line, once the system already has pumped water, then we're able to, the only other thing that we need with that then is a supply of compressed gas. And that can come from either a gas cylinder, which is less commonly used in surface water applications, or from a compressor. And that compressor can work with the compressors. The compressed gas that we use is primarily either air or oxygen, depending again on the treatment outcome that is desired in the application. So one aspect of this that we touched on a bit, but I'd really like to discuss a bit more and take a little bit of a deeper dive on is the charge and oxidation of the nanobubble. Excuse me. And so we have on the right hand side here, we have two different sort of forms of a clear nanobubble generator alongside a water body. And near the surface, when we're doing surface or near surface injection, really what we're doing is injecting those nanobubbles directly near the epiluminium of the water. And really this is the installation type that we would do specific to reducing or eliminating chemicals for algae control, and really keeping those algae levels under control. And this is due to the oxidative environment that's generated with nanobubble injection. And that oxidation, I mentioned this a bit, but the research that we've done both at Arizona State and other papers have come out on this, and the work that we're doing internally suggests that the oxidation that is generated, which is that reactive oxidation species, happens when that nanobubble collapses. So when it's injected into a water body, it is a stable, sort of higher energy particle, but it can react with things, and that oxygen reaction or stimulus can come from a reaction with chemical or with contaminants in the water, or a driving force from that dissolved oxygen out of the bubble itself. But as that bubble shrinks or destabilizes, that pressure in combination with the strong surface charge, that energy is released. And when that energy is released, it is creating reactive oxygen species, such as that hydroxyl radical, which can react and oxidize with things in the water. There's a really nice paper that came out recently, actually, on that, specifically tying that collapse of the bubble to the generation of that reactive oxygen species, leading to an oxidative stress, specifically on microcystis, and thereby reducing microcystis concentrations in a water body. Now, that was tied specifically to also to the charge of the bubble and how it's able to be modified to react with that microcystis. The other option, which I think is quite relevant to a lot of people here, is the sort of deep water injection of the nanobubble solution for elevating dissolved oxygen. And this is an application that we've been working with primarily in let's say primarily in smaller water bodies, so sub 5 acres probably. But in this case, it's really for addressing exactly what Mark was talking about in his introduction here about the elevation of dissolved oxygen, especially in elevated nutrient environments where the environments are very prone to going anoxic, and then resulting in sort of this almost ecosystem collapse in terms of the anoxic environment contributing to elevated nutrient concentrations, contributing to increased algae concentrations, which creates this very sort of hard to address negative feedback loop in an environment. Really, a water body that's just not able to be used by the community. And so when we're elevating dissolved oxygen levels strategically, whether that's across the entire water body, but in particular at the sediment layers where it's really important, that would be sort of a different type of installation for the nanobubble generator, where we're doing that injection at depth near the sediment layer. We spoke, I think, pretty well on the oxidation here. I honestly, I think this is one of the more exciting, perhaps most exciting aspects of nanobubble injection in terms of the oxidation that's introduced, that oxidative, we'll call it mildly oxidative impact that's introduced by the bubble itself. But if there's any questions on this, I'd be happy to follow up after the presentation. And we talk about oxidation in terms of how we can measure this in environment. We talk about oxidation primarily through the lens of ORP. And in this case, this is an installation that we had done, I guess this was last year now, looking at deep water oxygen injection for a lake. And in this case, you see that deep water ORP, which is a measure of that oxidation or reduction environment. We see that ORP shift from strongly negative to quite strongly positive, and we use ORP as an indication of that water body health, looking at how a negative ORP, which is often correlated with an anoxic environment. That negative ORP is also correlated with sort of undesirable microbial and chemical reactions, and can be related or correlated with not only nutrient release from the sediment, but also with methane production, sulfur production, which can lead to odors. And so as that ORP is shifted, in this case through the nanobubble oxygen injection, as that ORP is shifted from strongly negative to strongly positive, we begin to see more desirable microbial behavior occur, such as the nitrification and also the oxidation of metals. And that oxidation of metals is particular iron, which is very relevant to to nutrient sequestration or phosphorus sequestration. That iron is oxidized, in an oxic environment or in an ORP environment of around 200, approximately where that begins to occur. And we have some, just briefly on this one, we have various installations of oxygen injection, not only in surface water, but we also do this. This is very relevant. The same types of processes are very relevant in other applications as well, such as irrigation water and in aquaculture, of course, looking specifically to support fish health. The last application, or the last sort of property here that I want to briefly talk about is that charged surface. And this is really coming to play in a couple key applications where we're looking at the removal or scouring of biofilms from surfaces. And that charge of the surface, that bubble, actually really helps. Both the charge of the surface of the bubble and also the fact that the bubble behaves as such as a particle really helps facilitate the removal of algae from surfaces, particularly algae or biofilm from surfaces, particularly in flowing water applications. That flowing water is particularly important because of the sort of particle nature of that bubble, which helps scour or sort of remove a biofilm from the surface. And then in addition to that, we see that because of the hydrophobic nature of the bubble, and then also in addition to that, again, the negative charge, the bubbles tend to adhere to surfaces, and in that case, can help with preventing the readherence of biofilm to a surface. And this was an installation in the bottom here at a water park that we had done a couple years ago now, actually, looking specifically at the removal of biofilm in flowing waters. And I think this may be applicable in a couple different applications for those of us today. But in this case, we were looking at the removal of biofilm for the water park because it really was creating a hazard for the residents, and also, of course, it was rather unsightly. And in this case, within about 2 weeks of installation, we saw a dramatic change in the turbidity and prevalence of surface biofilms, or rather just biofilms, in their system. If there's no questions, we can just go into some case studies. I'd be happy to talk about how we've deployed a lot of this technical understanding and knowledge on nanobubbles to the field to create value in different applications. A lot of the work that we're going to talk about today is not only in ponds and lakes, but also in irrigation reservoirs. which is an area, it's a bit more controlled environment where we've been really able to understand the behavior of the nanobubble and the effectiveness and measure that effectiveness of oxygenation better. So the first application that I want to, or first sort of case study that I'd like to talk about today, and this is this is an irrigation reservoir. Actually, it's in Almeria, Spain. So this is quite common to have large irrigation reservoirs. This is 14 acre-feet. So this would be the size of many small to mid-sized ponds. And in this case, they were specifically looking at the increase of oxygenation as a pre-treatment for their irrigation water once it's brought into the greenhouse. However, this is extremely relevant also to the increase of oxygenation, even in natural water bodies or constructed water bodies, such as stormwater reservoirs and any pond or lake where there are nutrient concerns, especially around internal nutrient loading, although the benefits from nutrient reduction in externally loaded systems as well can be quite beneficial from the injection of oxygen, in particular if it's paired with, or in some cases paired with other treatments such as an enzyme or a microbial component to help stimulate that microbial digestion of nutrients, which is typically oxygen limited. So in this case, we have a 14 acre-foot or 17,000 meter cubed water body here. And in some ways, this is very representative of the traditional stormwater retention basin, but in some cases, or in some ways, it's not, in the fact that this actually had a fairly high, or I guess rather low, high turnover, low residence time, where all of the water in this water body was turned over about every 10 days. Now, the customer in this case wanted to keep this water body at above 20 parts per million of oxygen. Now, this is not uncommon in the irrigation sort of world or the irrigation space, especially for growers to keep their day tanks at above that 20 ppm dissolved oxygen level. However, this would be an extreme case for stormwater retention basins or other ponds and lakes where our target dissolved oxygen level really is just above that 5 ppm level. In this case, we installed a 1000 ppm recirculating system, injecting pure oxygen. That oxygen was generated with an on-site vacuum swing absorption oxygen generator. And so there's no need to provide continuous liquid oxygen, for example, or tanks or cylinders of gas to its application. And in this case, we saw the dissolved oxygen level increase from about 7 to 8 ppm. So there were not extreme anoxic concerns in this water body, but there really was an interest of the customer to drive those dissolved oxygen levels much higher. And in this case, we saw over the period of about 12 days, that dissolved oxygen level climbed from about 8.5 ppm, climbing steadily to about 24 ppm, which is what we had targeted in this installation. Now, there's something that was, this is a really nice case study because it's a very controlled water body, and we're able to monitor very closely what the dissolved oxygen response is and tie that closely to the monitored behaviors of the water body. And something that's important to note, and we see this even we see this regularly, especially in natural ecosystems and environments, is that we'll aim for a target dissolved oxygen levels, specifically tying an estimated oxygen demand with the oxygen that is required for that environment. And even in those situations, you see natural fluctuations between the target dissolved oxygen level and what's actually achieved. And in this case, we see that occurring just here. So we have that natural or the expected rise in dissolved oxygen, but then we begin to see a fluctuation, and that fluctuation is that about 4 to 6 ppm swing in dissolved oxygen. And in this case, this is due to what we would, I suppose, consider a flushing event. So a refilling, draining and refilling, or partial draining and refilling of the reservoir, in part due to irrigation water use, but also due to rain. So what we want to really achieve in a surface water environment is to keep that environment oxic. So really, we're not looking for 24, but rather closer to maybe 2 to 5 ppm of oxygen, but to keep it persistently oxic, especially for the digestion and processing of nutrients.
Hey, Christian, let me do a quick time check. We've got about 3 minutes left. And I know you've got more case studies, but wanted to see if anybody had any questions. I want to be respectful of people's time. I think we're supposed to end at noon. So hate to cut you off because I love the case studies. But
I appreciate that because my watch is running a bit behind and I would have gone for about probably another 10 minutes.
Great.
I appreciate that.
Yeah. Does anybody have any questions? I guess if you unmute and just ask, I think that works.
Hi, this is Mike Bradley. 2 questions. Number one, what's the beneficial life of this treatment? Do you have to constantly run it, or does it one application for a week or something and it's good for a year? And cost comparisons to like alum or dissolved lime.
So I'll just address that briefly here. The treatment, the nanobubble treatment, is, especially with oxygenation, is considered a continuous treatment. So we do prefer to have on-site oxygen generation equipped with that oxygen generator or the nanobubble generator to have that continuous treatment. And so that really does provide, it's a different type of treatment. That continuous treatment is a different type or method of treatment than, say, an application of alum, which is really addressing some of the nutrient concerns and clarity concerns in the water, but not really doing anything to, it's not a natural, sort of augmenting natural processes with the injection of oxygen. In terms of a cost equivalent here, it's difficult to speak directly to that because these installations can look so different depending on what or the type of installation that we're working with and the targeted treatment outcome. But I can actually follow up with a couple examples of that if you'd like to take that offline.
Thank you.
Are there any other questions?
I don't see anything in the chat box at this point.
Thank you.
We don't have anything scheduled directly after this, with the exception of the Region 2 caucus. So, I mean, if you want to continue and then wrap up at some point, I can also leave my link going because I'm not running the caucus meeting. Just a reminder that if you plan to attend the Region 2 caucus, if you are a delegate or an alternate, please sign on to that link that I have shared in the chat, and I'll actually put it in here again just in case you showed up late to this meeting. So the link is in there right now. Region 2 managers, please go to the caucus meeting because we need to take care of some business before the annual meeting this afternoon. But until then, feel free to continue, Christian, and I'll just leave my Zoom link on.
Sure, thank you. I think there's really one other case study that I wanted to talk about today. And I think the increase in dissolved oxygen from the irrigation reservoir in Spain here was particularly relevant to a lot of the issues that Mark had shared would be relevant to the audience today. There was one other case study here that I just wanted to briefly touch on. This is an installation that we had done in Chile. And I wanted to touch on this one because this was in part an oxygenation application, but also in part an algae treatment. And so the installation of the nanobubble generator, the solution was injected closer to the surface of the water. But one thing that we don't see, or sort of, I suppose, outside the scope of the nanobubble treatment is that of plants. And so we often like to pair, if we see a water body has not only an algae or an oxygenation problem, but also a severe plant problem, we need to pair the types of treatments to really address directly what the various problems that may be impacted or observed are. And in this case, we actually paired the nanobubble generation with the addition of carp to the environment, which really helped with the plant problem. And then when that's addressed, helps better distribute the nanobubble solution around on the water and helping to address the algae problems that were observed in this water body. And we saw this was really a very nice outcome from this treatment, where we saw with the carp address the some of the plant issues in this water body. But then in addition to that, the algae was addressed through the addition of the nanobubble generation, and the clarity overall improved. And I suppose in addition to that, nutrients are sort of kept in check, and the overall environment is kept in check here because of the sort of augmented oxygen ability with the water body. And I just wanted to touch briefly on this one because of the need for really to identify what the concerns are within the water body and what the treatment needs are, and then trying to pair that with an appropriate technology. And in the case of nanobubbles for oxygen injection and or algae control, it can be a very good fit here, but it does need to be targeted towards the desired outcome. So I wanted to touch on that one. I know we're running a bit late, and I appreciate everybody's time today. I'd be happy to take any questions here or offline. Feel free to reach out to me at my email that's on the screen here.
Any more questions? Ruth, I see that you're on this meeting. Can you join the Caucus 2 meeting? It's another Zoom link that's in the chat box. I've been getting messages. They're waiting for you. All right, any questions for Christian before we end this session today? They've been asked. I can put your email in here. I did actually share it with one. Oh, you got it?
I just added it. Yeah,
Okay.
thank you.
Beat me to it. Anybody else have any questions for Christian? Mark, do you want to wrap this up, or I'm not sure if Mark's still on?
I am here. Yeah.
Okay.
I appreciate everybody sticking around for an extra few minutes. I know it's a fun thing to talk about. And Christian, I know you had a number of other examples that are here in the across the U.S. Everywhere from stormwater irrigation, golf course, pond management, and so forth. But I think the question that you brought up a little bit ago, Mike, if you're still on, I think alum does work and has been proven to work, especially when you don't have carp digging up the bottom. But as Christian mentioned, it's a one-time application, whereas a consistent level of oxygen at the lake bottom is really what we found to be key. And that's why Christian mentioned having an on-site oxygen generator. But if there are some applications, feel free to let me know or get in touch with Christian, and we can talk through that. But I just appreciate everybody's time. This is it was years in the making during my time as in the watershed district, but now having a commercial application that's available is an exciting thing, I think, for all of us as people that want better and better water quality for lakes. So thank you again for your time. Appreciate it. And thank you, Maddie. Great job.
Awesome job, everybody. Thank you for attending today, and enjoy the rest of the day.